Am I audible? Okay. Good morning, all of you. Since we are studying about the sun from last 9 days, it's the final day, and I would like to present through my project whatever I have understood since these days. My project is on detection of chromospheric plages, and we were guided by our mentor Srinjana Raut. She is a JRF second year in Aries. I would like to begin with the basics of the sun, and then we'll proceed towards what exactly the project is. So this is a picture of a sun which shows different regions. Let's begin with the interior of the sun, which consists of convective zone, core, and radiative zone. If talking about the temperature specifically, as we go inner towards the core, temperature of the sun, the interior core of the sun goes on increasing. And while we are talking about the exterior solar atmosphere, it consists of photosphere. Photosphere is the innermost layer of the outer solar atmosphere, and it is the thinnest and the densest layer of the sun. We can see sunspots on the photospheric layer, and sunspots are a portion which has very high magnetic fields, which consist of umbra and penumbra. Next comes chromosphere. This is the second outermost layer, and it is comparatively thicker to the photosphere. And the next is corona. This is a very extended version of the outermost layer. And chromosphere is basically, if you want to see a chromosphere, we need to keep our eyes off the disk, because the disk is very bright and we might miss the very important features of the chromosphere. And we can see a thin glowing ring around the sun. Now, we have divided our project in 3 parts: what, why, and how. I'll be presenting what are plages. So here you can see a picture of the chromosphere of the sun, which is photographed using calcium 2K lines. And if I magnify one of the plage, this is the image of a plage, and you can also see some network bright points around it. So basically, what are plages? These are surrounded bright patches around the sunspots, or then there are sunspots in the neighboring sites of the plages, and they are associated with high magnetic fields. But you may ask, if I'm saying that sunspots have very high magnetic fields, why are they higher? These bright patches are higher than the surrounding of the other parts of the sun. No doubt, sunspots are the highest magnetic field portion available, present there. These are less, these have less high magnetic fields, but they have higher magnetic fields than the surrounding, and they are visible in H alpha and other emission lines. If we are talking about H alpha, we can say there are emissions of some colors, which you can also see in the background, that there are some colors which are emitted at the ring of the chromosphere. These are because of the H alpha emissions. And we can also see some prominent features of plages in calcium 4 emission lines, carbon 4 emission lines, sorry. Now, I would like to call upon Pranjali to explain why do we need to detect plages. Pranjali.
Hello. So hi everyone, Janvi already talked about what is chromosphere and what are chromospheric plages. She talked that plages have higher magnetic field as compared to their surroundings, but lesser than the sunspots. So all in all, because of this high magnetic fields, plages are considered to be part of an active region. Now, I will be talking about why we want to detect these plages, we want to track these plages. So considering this whole active region, if we get information about these active regions, we can relate them with the solar activity. So this is a very common plot that we see, sunspot number versus time. So depending upon how high sunspot number reaches during every other cycle or each cycle, we can draw some conclusion about the solar activity during that cycle. So instead of using sunspot number, we can also use sunspot area along with the plage area together, which means an active region area, and use it as a proxy instead of the sunspot number to draw some conclusion about solar activity. So this is one reason why we want to detect and track plages. Next, we can also extend it to long-term scales, I mean space weather and space climate. As Professor Durgesh already talked yesterday in his lecture about 0.1% variation of solar irradiance, meaning total energy output of the sun. So as sunspots are cooler, relatively cooler, and darker regions and plages are comparatively brighter as compared to their surrounding, overall, we can see, due to this, overall, we can see a 0.1% total energy output variation. Now, this output variation, as Professor Durgesh already talked, can actually have some impacts on Earth's atmosphere. I think someone talked about density variations, which can cause satellite drag. So these are the implications. This is also the reason why we want to track solar activity in plages. Lastly, we can also study the solar differential rotation. We know there are two kinds of differential rotation when we talk about sun. One is that the rotation period varies across the latitudes. And the second is that the interior of the sun rotates as a solid body, while the exterior doesn't rotate like that. So by identifying some features on layer, for example, plages on the chromosphere, and tracking them, we can get an idea about the rotation period of that layer. So this is just a pictorial representation that I was talking about. Next, let's just detect plages. So for that, we have to know what our data set at hand is. So we took data from the Solar Dynamic Observatory. A particular instrument on board was the Atmospheric Imaging Assembly. So this is just a GIF of that instrument. There are 4 telescopes on board. So this instrument takes full disk observation of the sun, and it covers a very broad wavelength range, starting from the UV ending at extreme UV, about 131 angstroms to about 4 angstroms. Now the images, the data set that we have at hand, they were in the form of images. Each image was divided into 4K by 4K pixel grids. And each pixel dimension corresponds to about 0.6 arc seconds. So that was the plate scale. Lastly, as I already told, the instrument covers a very wide range of wavelengths. But in this project, we have only used wavelength of about 1600 angstrom, which corresponds to the C4 emission line. When we usually analyze astronomical data, we usually do some sort of pre-processing on the data. But in this case, we already got 1.5 level pre-processed data. Someone also talked about this. So this just corresponds to the instrument or measurement sort of calibration and all that. So we didn't do any sort of level 1 or below that level of processing. Next, our data ranges for about 7 days, starting from 1st August till 7th August during 2014. And we have measurements for every 6 hours. So that is it about the data set that we have at hand. I would like to call Purvi to talk about the algorithm that we used.
So thank you, Pranjali. So as my fellow members very rightly explained about what are plages and why do we detect plages, let us now move into how to detect them. So the algorithm that we have used here is adapted from a previously used algorithm, Chatterjee et al. And the very first step in the algorithm is data prepping. So again, like Pranjali explained, we were handed down level 1.5 process data. Actually, AIA offers level 1 data, but the first step is this data preparation, which is actually done by our mentor. So the rest of those steps were followed by us. So after data preparation, the first thing we do is intensity clipping, right? So why do we do this? Because normally when we use SunPy to plot the SDO AIA data, we barely see any features or any solar disk at all. So this intensity clipping, which we use percentile clipping of the image, we do this to see what features we want to extract and what features we want to eliminate. So as you can see, like without any intensity clipping, this is what the data we get, and nothing is visible over here. But after intensity clipping, this is the data we have. So after intensity clipping, we see these large bright regions. These are the plages, and there's some background which is caused due to granulation or network bright points. But that is something that we don't want for our data. We want to eliminate that, right? So that's why we move on to Gaussian smoothing. Now for Gaussian smoothing, what is it? Basically, we use a weighted average kernel and we convolute it with the image so that each pixel kind of spreads out and smoothens out to larger areas. Okay, so for our curiosity purpose, we tried it with different sigma values to see what kind of effect it has on the blurring. So as you can see, like for sigma equal to 2, there is barely any effect of smoothing over here. For sigma of 16, you can see the background is blurred very nicely, but the shape of the plage has been distorted. So for our algorithm, we use sigma 8 value. Okay, now after Gaussian smoothing, now that we have smoothened out the background, we do intensity thresholding. Now, why is thresholding done? Because when we see a contrast of features with respect to the background, we do thresholding. Right? So we can see that in the original image itself, we saw that plages were relatively brighter with respect to the disk. So we do thresholding. So the type of thresholding we do is mean thresholding. Okay, so where we so when you plot the histogram of the image, you see the variation of the pixels with respect to the background. So you see this dual contrast over there. So with thresholding, we select a mean value where the values of the pixels are symmetrically distributed around the image. So here, so there in that equation, you see the value of k. So when you vary the value of k, the thresholding gives different results. So if we just selected right around the mean and we do not spread the sigma value over there, just at k is equal to 1, you can see this very noisy thresholding over here. You know, you can barely see the plages, and there is the background noise that has been selected as well. And for k is equal to 8, which is a higher range value, you can see all the plages are almost, eliminated. So again, for our algorithm, we choose the value of k equal to 2. So now that we have all that sorted out, sigma 8, k is equal to 2, after intensity thresholding, we move on to morphological operations. Now, morphological operations, again, these are done to detect out since plages are irregular in shape, we do morphological operations to extract those features based from the background or from the noise. Now, in morphological operations, normally you do 2 steps. One is opening kernel and a closing kernel. So in opening kernel, you mainly remove the hot pixels or the small white background noise. And in the closing kernel, you basically bridge fragmented images. So now, so that the shape of the larger area plages come out much better in the image. So again, for morphological operations, you can select different shapes of the kernel. We tried and tested with different kernels. So you can see for rectangular kernel of 20 by 20, size of 20 by 20, you can see the shape of the plage is been detected from the background, but you can see the sharp features over there because the kernel is rectangular, right? So and even if you select a larger size, then it is the plage is completely fragmented and it is not detected. Okay, so but for elliptical kernel, the shape of the plage is accurately detected, and also you can see this dark region here in this plage, which is basically the sunspot. So even that is accurately detected. So the area calculation from over here it would be much more smoother for us. So that's why we select this elliptical kernel over here. Now, after this, you can still see some network breakpoints over here in the background, right? Even after all these processes. So this is the last step of eliminating the background noise that we have over here. And for this, we do area thresholding, because as you can clearly see, the network breakpoints are very small compared to the plage area. So we do area thresholding. Again, so we had a reference area of 1 arc minute square to select a threshold area, right? But when we actually tried the threshold area of 1 arc minute square for this SDOAI data, a lot of the plages were actually eliminated. As you can see around the disk over here, there is this plage has not been calculated. Okay, there's a lag with the mouse. Okay, but and also for 0.16 arc minute square, there were some network breakpoints also that were detected in it. So the ideal, I mean, for our scenario, I wouldn't call it ideal, but for our algorithm, we chose the threshold area of 0.49 arc minute square. Right now, when we input this into the algorithm, we input it in terms of pixels using the plate scale conversion. Okay. Now, since all our plages are very nicely and smoothly detected, now what do we do with this data? We want to basically analyze the relative area of the plage with respect to the disk. So what do? We actually connect these areas that we have in each disk, and we take a sum of these areas. And for each image, like since we have 28 FITS files, right, which is for 7 days, and for each day there are 4 data points. So for each image, we basically take the relative area, that is the sum of the area of plages divided by the disk area. So this is basically the last step of the algorithm, which is the relative area analysis. And in the next slide, in the results, we will see what it exactly does. Okay, so first we actually, after the last mask that we got after area thresholding, we overplotted it on the actual image, and you can actually see, while as the disk rotates, how the shape of the plages and the area of the plages are changing over here. And in a more graphical sense, you can see it over here. So we plotted a relative area with respect to percentage. Now you might see that there are certain dips and rises in this data. And we might be tempted to conclude it is because of the magnetic activity. But since this is only a 7-day data, it does not give us any significant information regarding what that dip is or why that dip occurs. It could be because our algorithm might not be robust, or could be due to various other reasons, which we did not delve into. But the fruitfulness of this project was that we had understood how to detect plages and what role do plages play in various solar activities and the magnetic information that it gives us about the sun. So that's it. These are the final results. These are our references. And I would like to thank you, and I would like to thank our mentor as well for guiding this project.
Questions?
So you told that plages have less magnetic field compared to the sunspot. So do you have an idea what is the typical magnetic field of sunspot and plages?
I would not answer a very particular number, but at around 1500 or 3000 Gauss would be for sunspot. Around 450 or something is would be for plages.
And
Like
in one slide, see here you took data of 6 hours in time difference. Okay, so why you choose 6 hours? Is there any specific reason?
so usually the time scale or the lifespan of plages is only for several hours. So we wanted to see, we didn't want the what would you say, structure of the plages to change very much. So we didn't want to see that sort of evolution. That's why another reason would be that our mentor gave us 6-hour time span because of her own research. But one reason is that we didn't want the plages to evolve very much in terms of structure.
More questions? I had a basic question. What is the temperature range of the plages?
Temperature range of the plages. Plages are mainly studied because of their magnetic field activity impact on the sun. So during our 1-week project, we did not delve into the actual temperature range of the plages, but the chromosphere, yes, definitely. We had presented it in that slide, that the temperature range of overall chromosphere, because that is not the variation that we studied. So I'm not sure that yeah.
Okay, so have you studied why it is white?
It is white because it is bright. It is.
So there might be some, because of the temperature range, because of the temperature difference.
That is because there is higher emission in that side, but why it is just, I think, pseudo color, not specific to the
So it's big. It's
just
since
shows
it's
it
a
bright.
calcium to K emission disk, right?
Mm.
Overall. So based on the photospheric emission, we are not sure about this process though, based on what we have studied. So based on the photospheric emission, the disk absorbs it uniformly, but the plages absorbs it relatively lesser. So that's why it seems brighter with respect to the disk.
Okay.
But the brightness has no significant impact based on the temperature overall as such.
Thank you.
Yeah, in the equation for intensity thresholding,
Mhm.
the sigma is what? It's the standard deviation of the intensity.
Yeah, sigma is the
threshold?
standard deviation.
Okay.
Okay, I'll ask one. One of you mentioned about solar irradiance variation, about 0.1%, right? So will it be, that is the 0.1% is the peak-to-peak variation, but will it be maximum during the solar maximum or minimum during the solar maximum? How does it correlate with the solar maximum?
I mean, on a what should I say? I said the word variation because it
Yes.
could be higher or lower as well. But generally, it should be lesser in the solar minimum because there are less active regions. But I'm not sure, so I'll have to do it.
Yes, it is maximum during solar maximum. Even though you have more sunspots during solar maximum, you have more plages as well. So plages are exactly the reason you have more irradiance. So more questions? Yeah.
I'm not sure if this is right. So when we talked about the sunspots, so there was more magnetic field there, and therefore they told that, it was darker. The same is, even though the magnetic field is a little lower in the plages, again, the magnetic field is comparatively higher.
Hmm.
But then, why is it brighter compared to the,
So
sunspots?
it is brighter with respect to the disk. Right. So sunspot has higher magnetic field, but it seems darker because of the lower temperature, right? Because it kind of restricts the convection from happening. But plages are like more spread out magnetic field. So they are weaker than sunspots, but stronger than the disk overall. So that's why they seem brighter in the specific image of the disk, where we don't see sunspots.
Okay, so you're telling that, in the, this is more kind of spreaded in plages, while the other one, it is more constricted kind of.
Yeah.
So is that the reason?
Not necessarily that's the reason. I'm like, when you see sunspots, you see it in visible emission lines, right? So in visible emission lines, normally lower temperature regions will seem darker, right? But we observe plages in this calcium 2K lines, which is a very centered, very narrow band in that region. So for that region, plages absorb less of the line. So that's why they seem brighter with respect to the disk.
Okay, thank you.
I have shown a model in my presentation, if you remember, why bright points are brighter, whereas sunspots are darker. The same thing is applicable to plages as well. There are a bunch of small magnetic elements. But again, what Purvi said is also correct, that you have less absorption compared to the sunspots or other regions. Yes. All right, I think let's thank the group again. Okay, let's move to Suraj. You want to go next? We are running out of time, so let's stick to the 15-minute rule for each group. So please stick to your time.
Good morning. First of all, I and my group members, Suraj, Himani, Amrit, and Karthik, would like to thank you all for this opportunity to attend this workshop. We have utilized these 10 days to work on a project called MHD Numerical Simulation of KH Instability in Solar Plasma under the guidance of Dr. Balveer Singh. Now, I would like to start with our project. First of all, why and what is MHD? What is MHD will be dealt by Amrit here. Now, why MHD? MHD couples Maxwell's equations with hydrodynamics to describe macroscopic behavior. So basically, the tool we used can be used to utilize, to visualize any ideal plasma system, such as Earth's magnetospheric and astrophysical jets and accretion disks, but the background parameters such as density and velocity we used is specific to solar coronal plasma. Now a little bit about plasma. The ionized gas systems exhibiting collective behavior with Debye length much larger than its mean path length is called plasma. The MHD equations that we used can be applicable here if the given conditions are satisfied. If characteristic time is much greater than mean free path time and characteristic length is much greater than mean free path length, and plasma velocities are not relativistic. Now, Amrit will tell us a little bit about MHD equations.
Yeah, so the following are the ideal MHD equations that we have that are governing our simulations, because we have assumed ideal conditions. So starting with the first one, that is the continuity equation. Well, this this is based on the law of conservation of mass, as you can see, the first equation is the in the conservative form. So if we why is it not pointing? So whatever. So the second, if we can expand the second term into two terms, this term here basically represents the change in the density in the direction of V. This is the advective term, and this is the compressibility term. As you can see that the value of del dot V basically represents the compressibility, whether it is positive, negative, or incompressible. Going to the conservation of momentum equation, this is based on the Newton's law in the fluid, where we can again expand this term into two terms, where this term basically represents the magnetic tension, and this term represents the magnetic pressure term. So going to the energy equation, again, this is the energy equation where we have this energy E, where this term basically represents the internal energy due to the pressure. This is the kinetic energy, and this is the magnetic potential term. This is for also the P dash which we used. So this is also in the conservative form, as you can see, in the similar way, that is change in the some quantity is basically and the sum of that divergence of that quantity as well is equal to rho v dot g, because there is gravity due to the mass here. Moving to the induction equation, this is again derived from the Maxwell's equation, that is the del B by del T1, where we have also used the modified Ohm's law, and thus finally we got this equation. By the way, because it is ideal MHD, so here the conductivity are assumed to be like in very large. So sigma basically tends to infinity, and in general you will find the diffusion term here, which is basically eta del square B. But because eta is inversely proportional to the conductivity, therefore this term can be neglected in our ideal conditions. And this is the very familiar Maxwell's second law, that is the del dot V is equal to 0, which basically encapsulates the idea that magnetic monopoles do not exist in in nature. And finally, again, this is the very familiar ideal gas equation. You might be familiar with the PV is equal to nRT form, but of course here basically V is equal to like rho by m, and this is basically for the single particle. So P is equal, this is the equation that we have used. So now I will ask Himani to explain further.
So the base of the presentation on which we are performing the MHD simulations is Kelvin-Helmholtz instability. So first of all, what is instability? Like it is the state of being unstable is instability, and the Kelvin-Helmholtz name because they firstly discussed about this phenomena. So KH instability is a fluid instability that occurs when there is a velocity share in a single continuous fluid or a velocity difference between two fluids. So this is generally vortex shape, and it forms at the interface of erupting CMEs and coronal jets. So as you can see in these figures, in this animation, that two fluids are forming vortex shaped structure. And similarly, the clouds here are also representing the KH instability. This is the example in Saturn. And here in this figure, two fluids with different velocities are producing vortex shaped structure. Like this negative sign here is representing that the pressure is decreasing in the direction of instability. And this gradient P creates a pressure difference between these two different fluids, and due to this pressure difference, both these fluids accelerate towards each other and form the vortex shaped structure. So now I would like to hand over to Karthik.
Thank you, Himani. Moving to our next topic. So, as we learn about the Kelvin-Helmholtz instability, so that's the problem that how we solve this problem by using the numerical code. So we are using the Pluto numerical code, which is a finite volume numerical code, which is designed to integrate the MSD equations and to solve it by in conservative form. So there are general steps for this numerical code. First one is the initializing the initial and boundary configuration. Second one is the initial configuration. And third one is the executing the program. So first of all, we normalize the unit and dimension. In this numerical code, there are involved some of the parameters like length, density, and energy. And due to the introduction of this parameter, we have to specify the basic units. So there are three fundamental units here: unit density, unit length, and unit velocity. So as our field of interest is solar corona, so we specified these factors like unit density is 10 to the power minus 15 gram per centimeter cube. Note that we are using the CGS units here. Unit length is 10 to the power 8 centimeter and unit velocity is 10 to the power 8 centimeter per second. Next one, if we have to simulate any diagram, we have to do a simulation domain. So for a simulation domain, we have to specify the spatial resolution. So in a spatial resolution, we have to first of all decide which pixel we want to create. So pixel, or we can say grid spacing, we decided we will go with the 25 kilometer per numerical cells. So we decide that in X direction, we will get a range of -2 to 2. That is the 4 megameter distance. And in Y direction, we decided -3 to 3, which is 6 millimeter distance. And to get a 25 kilometer per numerical cell, we calculated so that the resolution we got is 160 by 240. So this is the grid resolution we got for the simulation domain. In temporal resolution, we show it the output data for 1 second, that we get the output data in the interval of 1 second. In the case of the boundary condition, there we have put the X direction in the periodic way. From left to right, it will be periodic, and from top to bottom in the Y direction, it will be the outflow. Now, the initial configuration, as we have discussed that in the Kelvin-Helmholtz instability, there he mentioned that it has a different densities and different velocities. So if we have to decide the configuration, so we have to focus on the initial velocity and initial pressure with the consideration of two different densities. So we have taken the two densities here and the velocities with the hyperbolic tangent profile and the sinusoidal profile, so as to get the interface in the domain. Why? Because as we have seen here, so this instability happens because of the two different velocities. So if we have done the sinusoidal sinusoidal nature, so it will be a disturbance occur in there. So we can actually study that instability with our parameters. So this will look like this. So I call Suraj to discuss the result.
Hello, everyone. So let's start with the results. So yeah, this is our result. And here we have applied a magnetic field in the X direction, which is around 1.12 Gauss, a typical value in solar corona. And then we let the simulation run. And for the first 2 seconds, we didn't see much changes. Hence, we have not given the output for first 2 seconds. So this is the output at 3 seconds, 4, 5, and 6. And as you can see clearly, the vortex forming in 6 seconds. And then we tried to change the magnetic field angle there. And we applied the magnetic field at 5 degrees to the x-axis with the same magnitude. And as you can see clearly that it has a suppressing effect on the vortex formed here. Hence, the magnetic fields have a suppressing effect on cage instability. With this, I will move to our conclusion. Okay. So like from this work, we saw the evolution and dissipation of cage instability using the MSD model. And we got to know like which all parameters we need to fix for this model in the Pluto code. Then along with that, we took a 2D flow and which were parallel, and a magnetic field was applied and we studied it numerically. Finally, we studied that how the angle actually affects like how it has a suppressing effect on the vortices. Also that the cage instability is very important in the solar atmosphere for energy transport. And in further, we would include non-ideal terms like this simulation, everything is ideal MHD. Hence there we will include viscosity, thermal conduction and resistivity also. And then we will maybe help to get some significant results out of it. Thank you. Oh, yeah. These are our references and thank you so much. अब सही लग रहा है.
Okay, questions? Any questions?
As Karthik mentioned about Pluto code, you talked about the finite volume approximation that you have used. So can you tell about the finite volume thing? Basically, if we specify yeah, spectrum simulation domain, so where there we configure some of the initial value and the configuration that I mentioned, the initial velocity. So the initial we took the consideration that the velocity should confine in the boundary condition so as to get so as to get the result that how velocity will affect in the specified boundary. That's why it is called the finite volume.
Okay. More questions?
In the results, like it was shown till some 6 seconds, right? Yeah. So what generally happens? Does it stay the same or like?
Actually, we have not simulated further because it takes 3 hours for one simulation.
Okay. Okay. So, okay.
Okay. What is the plasma beta of your simulation? You know what is plasma beta, right? I suppose, right? Okay. So I'll ask another question. It's fine. So in one of the equations, I don't remember which one of you, but some of you mentioned about the different terms in the energy, right? So in one of the equations, can you show that slide? Next one. Yes. So what is there? It is mentioned. Is it the energy terms on the right side? On the right side, what are the terms there?
Well, they are the.
So what is v square by 2 mu? The last one.
They do represent the energy term indeed. Like this one is definitely the kinetic energy term. And I checked this is also having dimensions similar to this. So analogously, this is also the energy, the magnetic pressure we call it.
So it is pressure, but it is energy density. It is not just energy.
Yeah.
So if you take the energy density, then you will get pressure. So in terms of this is gas pressure on internal energy, and then that is magnetic pressure. So this is also, you can see rho v square, it's not mv square. So it is energy density.
But having one per volume.
Yes. Okay, that's fine. Any more questions? Okay, if not, let's thank this group. Thank you very much. So next group, who is presenting? Let him know which one is your
No. इससे पहले वाली यहाँ
ये नहीं है कभी बोल रहा है ये you don't remember the file?
सर ये बताइए Good afternoon, everyone. Today we will discuss about the analyzing line spectra from simulatory data. My name is Shakti Singh, and these are our team members: Sribala PS, Krista El Salinu, and Deepa Berthwal. And our project guide is Ambika Saxena. We have done this project under the supervision of Ambika Saxena ma'am. She is JRF here, doing PhD here, and in this presentation we will discuss about the what is solar spectrums, what is spectrography, and how we will use in this solar spectrums, and what is spectral bonding, and all these parameters we have discussed in these presentations. So we are going to the introduction. We will discuss about that. We are here. We all are aware about the solar physics. We are here for the study of sun. And what if possible? What can be the consequence if we didn't discover about the spectroscopy? If you will not discover about spectroscopy, then what changes are in our studies? So we had till now. So I will discuss and I will put light of the spectroscopy. And what is spectroscopy and how did it discovered? This is a historical parameters, and all of you already know about what is spectroscopy, but still I will give a brief introduction about the spectroscopy. It is a study of the spectra produced when matters interacting or emitting electromagnetic waves. There are two types of spectra, like continuous spectra and discrete spectra. In continuous spectra, we will get the wavelength, all the wavelengths of light, and in discrete spectra, we get emission spectra and absorption spectra. In 1814, Fraunhofer, he used a high intensity, or we can say that high quality prism to diffract a beam, and he got some dark lines. That is the first time anybody goes at dark lines. Then he discussed, then he concluded that these dark lines are why we are getting these dark lines. So he get a conclusion that these dark lines are like we are seeing here that we in emission line spectra, we are seeing that these bright lines or dark lines, and absorption line spectra we are seeing that these lines. Then when a electron jumps from a level to another level, it absorbs some energy, and when he come back to the level 2 to level 1, it emits some energy. So when it emits some energy, that there is a emission spectra, and when it absorbs some energy to go to the next level, it is absorption spectra. So here we'll discuss about the coronal emission line spectrums. So as Krishna sir discussed about that, we cannot study the corona directly. We have some coronagraph or we have some occulter to cover the disk of the sun, and then we can get the knowledge of corona. How is corona expanding, and what are the things happening in the corona. So here we will discuss the corona have a region of extreme ultraviolet wavelength. These wavelengths are very shorter wavelengths, so they cannot reach to the earth directly. So we use some space observatories to study the extreme ultraviolet wavelength, which consists of ultraviolet waves and X-ray waves. So in this PPT, we have we can say that we have a emission spectrum. Here we are getting more lines of iron spectra, and in this project we have used iron 13 to study the properties and parameters of iron 13 spectrums. And then what is the question is, what is line spectra? This will tell us, it will explain by my teammates, Ms. Deepa.
So now I will discuss about the line spectra. What is line spectra? Line spectra is a spectrum formed by the absorption and emission of light of certain wavelength. And depending upon the absorption and emission, these are of two types. First one is absorption line spectra and another one is emission line spectra. So in absorption line spectra, what we can say, the electron of any atom is absorbing the energy that we have given to it, and it is going in the higher energy state. So we can see the absorption line spectra of hydrogen as an example here. And the other one is emission line spectra. This is formed by the, we can say, emission of energy that is radiated out by the electron after coming from higher energy state to lower energy state. So now we will discuss about the spectral broadening. So the observed spectral lines are always broadened. We can't see the sharp spectral lines that we can see here. So what are the reasons for the broadening of the spectral lines? So there are basically two to three reasons. First one is the natural broadening, which is due to the quantum mechanical properties of electron. So the energy that is required by the electron to jump from the lower energy state to higher energy state is not exact, due to the uncertainty associated with it, as we can understand it by the Heisenberg uncertainty principle. And the other one is the Doppler broadening. This is due to the relative motion between the observer and the source. And here we can see the formula that we have used for Doppler broadening. And this is the broadened spectral lines. So now I will discuss about the parameters of line spectra. Here we can see a Gaussian distribution that we will be fitting across the spectral line. So here the intensity is showing the peak intensity of our spectral line, and the width is corresponding to the line width associated with the spectra. And it is centered around the central wavelength. And these are the important parameters associated with any spectra. And now we will discuss about the data analysis part.
So I'll be talking about the data we used in the project. So we have used a stimulated data for this project of a corona. So from the inner corona, we are moving radially up around 50 megameters. And that is the diagram I've shown here. So we are moving up around 50 megameters. So the patches you have seen, that is of the solar plumes. The solar plumes are like thin ray-like structures. And over the next B diagram, you can see the density getting reduced because of the gravity presence as we move up radially. And the stimulated data are of 3D transverse MHD stimulations of propagating waves in the open field regions. So the output we get from the MHD stimulations are given as input for the forward modeling. And from the forward modeling, we'll be getting a spectroscopical output. From the spectroscopical output, we'll be finding the specific intensity that will be used as the data for our project. So the data was given by a mentor. So we have plotted it as a distribution first, then fitted it over a Gaussian curve. The equation we used is shown here. Here, the I naught represents the peak intensity, lambda shows the observed centroid, lambda naught shows the central wavelength, and sigma shows the standard deviation. So after we have done the Gaussian fitting, we need parameters to get in the final result. For that, after Gaussian fitting, we got 3 parameters, that is the mean, sigma, and amplitude. From these 3 parameters, we'll be evaluating intensity, Doppler shift, and line width for the data. So about the results, I'll be calling Srivala.
Hi, everyone. You might have noticed what is the aim and objective behind our presentation and our work. And as far as we know, we have done the curve fitting methods and the simulation experiments, and we have arrived at some valid and very informative conclusions that we have learned as a part of the project. And you may notice that the first and the foremost part we did during the presentation, during the project presentation, was the curve fitting method. And curve fitting, as you know, is a very basic tool in case of spectral analysis, which helps us to get more interpretations regarding what all parameters will be suitable for explaining our studies. And we have 4 people in our group, and we have done 4 kinds of data sets showing curve fittings respective to the selected data. And you might see the different data observed and the Gaussian fit that we have taken for as a parameter for curve fitting. And these are the observations that we got. And you, as far as you have listened to the broadening parameters or broad line broadening, you might see how this kind of fitting is important for us to obtain what you say, the line width or the intensity maximum or the Doppler shift or etc., which you find soon why we need this. And these are the primary data analysis technique, primary kind of what method we use for the spectral line fitting. And coming on to the second part was our identification of the other parameters, and the main parameters that we have used for intensity, Doppler shifting, and line width. And first we'll be discussing some valid informations regarding the intensity profiles. And you might see that the major equation that everyone may be aware of, as if you have a maximum intensity and the standard deviation, as you may observe from a given data set, you can use or you can find the total intensity using the equation 2 pi I maximum times sigma. And from this equation, we have stimulated and we have obtained the following 2-dimensional images. So it may be a common question of pondering that why you have taken 2-dimensional images, but we have used a 3-dimensional stimulation. So it is taking into consideration that, as you have observed while the forward modeling data was discussed, it is a stimulation cube having 3 dimensions, x along x-axis, along y-axis, and along z-axis, representing the radial dimensions and the plane of figure dimensions. So we have taken here the plane of figure as x dimension and the radial dimension, so that your curve or your plot will be almost longitudinal in shape. So this curve or these images can show directly how your intensity profile is getting varied. So you might see there is a variation that we have selected from over a range of 0 to 20 centimeter, and remaining in sec per second per radian per angstrom and all. And you see, you might observe that the white areas corresponds to low intensity maximas, and the darkened areas towards, as you reach up to a profile of 20 or something, you might observe dark intensities. So what this particular kind of representation is to show you that there is a kind of density in homogeneity that we can observe in our simulation experiments. And you might see that these intensities are these intensity fluctuations that you might observe right now are very important and crucial to the study of this density in homogeneity in our simulation. And you also observe that there is a kind of swaying motion. That means our cube of stimulation is is given a wave propagation, so that the what you call as the solar filamentous, the solar structure, coronal structures you can see as waves. These are propagating along this longitudinal directions, and that's why you observe a kind of swaying motion throughout these different intensity profiles you have seen analyzed by different members of our group. So that's about the intensity profile. You can see if you are taking a time series diagram, means you could have clearly obtained a saying moving picture of these data profiles of intensities. So that's it about intensity. Coming on to the next parameter is the Doppler shift. As you might see that the Doppler shift parameter range we have taken is approximately -20 to 20. And this is just for the ease of the observation of how these profiles vary, and not
completely according to the scale. So you can see there are areas of blue shift and red shift. And the basic equation, you might know how a Doppler shift is. It's basically delta lambda by lambda into C. And the lambda 0 we have taken is corresponding to iron 30. And it is approximately 10749 angstroms, as you might have noticed. Okay, so what this Doppler shift is indicating is that you have taken the patch of the area, and you might see these what you call as the coronal waves may be propagating along the longitudinal direction, and this might lead to the displacement of the plasma constitution or the plasma structure itself. And as a result, as far as an observer views from the line of sight, you might notice there is a shift in the velocities or shift in the wavelengths, and this corresponds to the Doppler shift as far as the observer sees from his line of sight. And this line of sight variation may also lead to the shift in Doppler shifts or the changes in Doppler shift, which is dependent. So you can see in the first data set, you might have noticed there is a very specificative indication of how blue shift and red shift comes, and you can currently differentiate it. A part of the waves is moving towards the observer and the rest is moving away from the observer. That's what you can see as blue and red shift. And I'm sure you might have understood what a red shift and blue shift is. And coming on to the second interpretation, you can also see that there is a kind of red and blue shift, which is observable. But coming towards the last two data sets, you might feel like there's a complete shift towards the red end or complete shift towards the blue end. And that corresponds to the fact that the corresponding data set, what we have taken is displacing the plasma either away from the line of sight of our observation or towards the line of sight of observation. And we cannot see the same at the, we cannot see both at the same time. So that's why we have got 4 different kinds of Doppler shift profiles. And coming on to the last parameter or the last observable parameter, we have is the total linear width. As far as you might have noticed in the line broadening slide, you know how crucial is to analyze the linear width of the spectral line. And you might be familiar with the equation of the total linear width. And what we have observed from our kind of performance of the project was like this plots of linear width, which shows that there is a gradual linear width variations, which is a clear indication of the Doppler broadening, because coronal waves mainly what takes into account, the corona mainly has a Doppler broadening, which is very prominent due to this Maxwellian distribution. And we know we have taken that the linear broadening here corresponds to the non-thermal broadening. And that's why we have got a line width corresponding to different ranges. And the range we have taken varies over from 40 to 75, again taken according to the scale of each of our experimental observations and all. So that's how we find the total linear width profile or line width profile varies as per our data observations. And coming to the conclusion part, as you have know that this is a basic thing that we all know, that the curve fitting and Gaussian fitting and all is very crucial for the analysis of any line spectra, and it is considered to be a very important and basic tool before coming on to the any advanced experiments or advanced data handling sections of what you call in astronomy or astrophysics. So what we have learned from this experiment is to enhance the basic understanding of our idea regarding Gaussian fit, curve fit, etc. And two-dimensional plots obtained from the simulated data, different spectroscopic variables, and also from the valid informations that we have taken, we were able to relate or correlate or explain or get ideas regarding line of sight, the dynamics, motion, density distributions, and all regarding the coronal structure and all. So that's what our project deals with. And I would like to thank our project aide, Ms. Ambika Saxena, for giving us this opportunity to work more on the very basic approach towards this, strengthening our approach towards the basic and most important aspect of spectroscopic analysis. That's all. Thank you.
Yeah, actually, one important part was missed that I want to clear that she has explained the simulation queue, but one thing was forgotten that this simulation queue was driven from the bottom, and the wave propagation part. Then I think she came and told about wave propagation. So I mean, the cube was driven in the simulation from the the bottom of that cube was driven, and kink waves were passing were propagating throughout the cube. So whatever the these profiles they obtain, they have the effect of that kink wave passing through these density inhomogeneity structures. So that is something that was missed, so I'm really sorry for that.
No problem. More questions?
I just couldn't understand the data simulation part. Can you please go through that? I mean, it was like,
Yeah, so first, the MHD equations are solved to get rho, density, and other variables for MHD equations. And those equations are given as the input for forward modeling to get the spectroscopical output that we need for this data, that is the specific intensity.
so your simulation box has emission is particularly simulating for the emission line centered at that particular value, right?
Yes.
Yeah. So any particular reason for choosing that emission line?
It was for iron 13, that's specific lambda. So it was given to us by the mentor for that specific. And I think for the corona, it's mostly from iron 13 and other waves like X-ray and UV. So with that specific reason, maybe I might have choose the iron 13 over this.
Actually, we haven't worked upon that regard, but as far as I consider, I think it is the best, like more fit. It is the best option that we can obtain this sharp lines or something corresponding if we take iron 30. I'm not sure.
Older of the lights, like visible and IR observations are there since longer for corona. So only when during the eclipses observations were the first, right? So later only when we went to space, then you have these UV observations. Before that, to observe corona, you have to observe either in visible, infrared, level. So that is one of the old observed laws. So still you can see the even in iron 13 there, since that corresponds to iron 13, you can see the corona variation. So more questions? Yes.
Yeah, I just need a clarification regarding the plots, like the radially upwards direction in the corona is marked as X or Z.
Actually, from the stimulation cube, you can see x-axis and y-axis is facing towards you, and the z-axis is facing away. I mean, is the x-axis is facing away from you towards the board? Is the length along the longitudinal direction, and the x, y, and z is facing towards you. So I have taken what as the x and x-axis and z-axis, so that you can see like there is a linear variation of this kind of corona plasma shift and all. How you can actually see how these waves are moving only if take it along the radial. Yes, this is a snapshot, but in the intensity profile.
Yeah, my question is like, how does the distance from the center of the sun to like corona map here? Does it?
Which coordinate the
height? X.
Okay.
So what is the direction of gravity here?
No, direction.
Yeah, we could written the presence of gravity is considered.
Yes. Yes.
What is the direction of gravity?
Maybe
You just
Two.
asked the question. You can answer the question previously.
Okay. Minus x-axis.
Minus x-axis. And what is the effect of gravity here?
Effect.
So let's say if you ignore the gravity, what will happen to these plots? What will change?
Z-axis wouldn't have been extended. X-axis wouldn't have been extended.
Wouldn't have been explained means what? You can always have x-axis, whatever you want in simulation. But if you ignore the gravity here, what will happen?
Okay.
The density shift won't happen. So,
Density?
the plumes are having a density shift that will take it radially up. If they're not considering the gravity over here, the density difference of the plumes won't be considered.
The difference where? Across?
Across in the deep river, across the radially up direction.
So there won't be any density stratification.
That
So I wanted to ask, I mean, I don't know if you've mentioned it over here, but do you see any continuum in these emission lines that you see? I mean, if there is, then do you normalize it and then measure the broadening? Or
Oh, this is just emission line spectrum.
so no continuum as such. And
No.
why? Because you're measuring broadening, so why do you choose Gaussian fit as such? There are other types of fits also there.
Okay, there are other
measure
fits like
broadening.
Laplacian and you mean Laurentian.
Laurentian or
Okay.
white or
Actually, we this Gaussian fit best fitted for our data during the modeling technique. That's why we suppose it is. We haven't been much into that.
Right, but broadening, right? So Lorentzian would also help you measure the broadening, right? So why exactly Gaussian?
I'm not sure I'm now able to answer.
I think the particles in the corona follow the Maxwell-Boltzmann distribution, and that is the best fit if you use the Gaussian fit for it.
Okay.
So the natural broadening you mentioned, that follows the Lorentzian.
Yeah.
The Doppler broadening because of the particle distribution that follows the
Yeah.
And then you have the Doppler broadening to maximum component. That's why Gaussian is better.
Yeah. Okay.
So I think let's thank the group. Who is there next? ये 15 मिनट चलेगा
15 मिनट चलेगा
हाँ तो ये तो ग्रुप तो प्रेजेंट करेंगे तो फिर उसके बाद 1 बजे तक तो मैं वही बाद में लिखा था मैं
अच्छा आपने लिखा था
हाँ ये प्रेजेंटेशन चल रहा है
नहीं है इसलिए मैं आ गया मेरे को लगा कि लास्ट वाला
प्रोजेक्ट प्रेजेंटेशन Aditya-L1
अब आया नहीं आप सर्टिफिकेट दे दो
हाँ
मैं देखता हूँ मेरे को जाना है
जाके वापस आओगे तो
आई थिंक वो रिव्यू कर रहे थे
मैं वो कंक्लूडिंग सेशन नहीं है ना मैं वो
आप बोल देना
बोल दूंगा बस और कुछ चाहिए और कुछ नहीं है ना
मैं इनको को फिर लंच में मीट कर
ठीक है तब तो ठीक है Hello. So is this the last group or do we have one more group? Please go ahead.
Hello everybody, good afternoon to all. Today we are going to present our project about characterizing the CME using J helioviewer. My teammates are Sunil, Akanksha, Disha and Ritika. My name is Karan. And this project is mentored by our mentor Nitin sir. Okay, so these are our outlines, which contains different layers of sun, coronal mass ejections, J helioviewer, CME observation results, summary and future scope. So I will basically discuss about the basic why we are choosing the CME and the basic outline of sun. That is, we are all familiar with the layer of sun, that is from the core to radiative zone, convective zone, and then the visible outermost layer is photosphere, And then which starts is atmosphere of the sun from the chromosphere corona. And why was interesting about coronal mass ejection is that whatever with the geomagnetic storm that's driven by the sun's activity, the major geomagnetic storm, that intense geomagnetic storm, is driven by the coronal mass ejections. So by definition, it says that discrete bright white light feature of propagating outward in coronagraph field of view for a time scale up to several hours. That is the definition of coronal mass ejection as we are seen from the Houston et al. 1984 paper. So the three-part structure of coronal mass ejection is as we are familiar with. First is from the top view leading edge, cavity, and core. This leading edge consists of this compressed plasma. This cavity consists of this helical shaped magnetic field length that we are basically called with magnetic flux rope. And this core is basically filament of prominence, that bright patch that you have seen. And these have a various effect. Leading edge have various effect on when the CME reach to the earth, because this is compressed plasma. Cavity, because of this cavity, there is a magnetic flux rope. So when it will reach to the earth, then there will be a magnetic reconnection and geomagnetic activity happening. Density enhancement, and this magnetic field increases suddenly. This kind of effects we are say it as a geomagnetic effect. So
So now we will, in this slide, we will talk about the SOHO spacecraft. So it was launched in 1995 and it was a joint mission by ESA and NASA. And like SOHO spacecraft has, I think, around 12 instruments. But for this project, actually, we have only considered the LASCO C2 and LASCO C3 instruments. LASCO C2 has a range from 1.5 to 6 solar radius, whereas LASCO C3 has the range is from 3.5 to 32 solar radius, and they both continuously observe the sun. Cadence of the LASCO C2 and C3 is 12 minutes. And like I already said, like we are using the CME data set of SOHO, LASCO C2, C3 coronagraph for this project. So actually, this is the J-HelioViewer interface, actually what the first pages look like. And this is the interface of that software, UI software. So okay, so actually this is the UI which we have used for our project. And in this UI, if you will observe, then we can give the timeline. Actually, what we have done, like we have taken the CME from the CDOC data, and then from that, we have considered one date and one specifically time to observe the CMEs. So in reason, you can see that we can put the date and with a particular time, which of the CME which we want to observe. Then in the new layer, we have added the LASCO C2 and LASCO C3. There is one drop down option you can say here. In this, actually, we have used the SOHO database. So from that, actually, we have chosen the LASCO C2 and LASCO C3. After the uploading of the data, we can find the leading edge. We can see the leading edge here, means the data will be visible for us. And this is the this area belongs to the C2, and this area belongs to the C3 part. Now for this project, what we have done, like if you will see, so like we have taken one particular angle, and here is the angle, like you can see 52 point something 83 degrees. So for one particular angle, we have taken the solar radii actually, means the data which we have plotted for a one particular constant angle between the solar radii and the time. Means so this was our thing. And like here there are many different options which are available. Like you can use the you can observe the data in the different kind of a wavelength, and there are many database which are available to observe this, but we have observed this only actually.
We talk about the CME observation. CME are primarily detected by coronagraph that block out the majority of light from the coming from the sun. White light is corona due to Thomson scattering. We have to detect the CME at a particular particular angle and 3 parts of the CME.
How to post a video actually.
3 parts of CME, leading edge, cavity, and core. In second video, we have to detect the CME at a particular angle. Yes. Huh. 3 parts of CME, leading edge, cavity, and core. And we have to detect the CME at a particular angle.
Okay, so previous 3 videos were that we have taken the data and those videos we just play. So the result part, what we have done is after taking data from J. Helio Weaver, what we have done is so we plot the one linear fit and one quadratic fit. So the upper graph is height versus time. Here height is in solar radii and time is in minutes. So the linear fit which give us average velocity, and the quadratic fit which give us average acceleration. And similarly, we have done for instantaneous velocity and acceleration, and the below two graphs are for instantaneous velocity and instantaneous acceleration versus time. And here is the error bar which we have calculated from error propagation. So this was the one event, and similarly for 2 other events we have done the same, apply same method and got this result. Okay. Yeah. So similarly for other 2 events we got the same results, and yeah. And this is our table of result where we have tracked 5 events. Dates are mentioned here, and we got the result, average velocity and average acceleration. And yeah, so summary part will be delivered by Deepika.
So in our presentation, we have talked about different layer of sun, and then we have talked about what is a CME. Then our aim was to recognize the CME by using J. Helio Weaver software, by using LASCO C2 and C3, which is a corona graph on spacecraft SOHO. Then we have to calculate. We had calculated the average velocity, average acceleration, instantaneous velocity, instantaneous acceleration by plotting the height and time graph, velocity time graph, and acceleration time graph. Then the field of view of LASCO C2 is 1.5 to 6 solar radii, and the field of view for C3 is 3.5 solar radii to 32 solar radii. And LASCO, as we know that LASCO C2 start from 1.5 solar radii, so we don't have data from this region. So thanks to Aditya-L1, which will help us to give the data in this region. So VLC is a coronagraph, which is a payload on Aditya-L1,
visible emission line coronagraph. This is the references. Thank you.
You talked about finding errors. How did you find the errors?
Okay, so we have calculated error through like we have formula like if y is equal to x by t. So we calculated error from this formula. Or mentor said this. You can use.
Any more questions?
So you said from the plots you calculated these instantaneous velocity and instantaneous acceleration. So which plots give those kind of values? Like from which plots? What is that? That was not correlated, as in, like you have the velocity height time graph, velocity time graph, and the acceleration time graph.
Yeah. So acceleration time graph gives us instantaneous acceleration, and velocity time graph gives us instantaneous velocity. And the upper height versus time graph, from there, after doing linear fit, we will get average velocity, and after doing quadratic fit, we will get average acceleration.
Average acceleration.
Yeah.
Because
Okay.
the average acceleration is not something constant. When we have calculated average acceleration, we get a single acceleration of km, but that is not the actual case. Km initially accelerated. So we have to calculate the instantaneous acceleration. And so when we are
Yeah, so but if you do perform a quadratic fit on the height time graph, from there also you can get the instantaneous velocity. Right. So why use the velocity time graph?
When our mentor
That's it.
do this one.
The average velocity and average acceleration, actually these were the means values which we need to find, and was instructed by the mentor that we have to find. That's why we have find.
Okay.
It's not any kind of a particular thing.
Okay. Sure.
from the position that we calculate.
Yeah. Yeah. Okay. Yeah.
Yeah, so the CME, I will ask a very basic question. So in a CME, you see the leading edge, a cavity, and a core part, right? So can any of you tell me why the leading edge appears brighter? Why?
Plasma or like plasma.
Leading edge that concept of complex plasma, whenever the same is up, suddenly there will be a complex plasma about that. So that is happening that because of them.
Okay, good.
I've seen in other presentations also, there is this specific sort of shape in the height time graph. I mean, they said that they usually fit a linear curve to that, but could there be some other information that could be derived from that particular shape? I don't know. There's a very constant part, then a bump of some sort. No, the
Like
height.
from here.
This one. No, not in the next graph. I've seen this sort of a jump in various graphs. Is this something that happens, or am I just making it up?
Value which we have taken. Actually, we have taken the value for a particular angle, and on the basis of that, we have taken the height time, the solar radii and the time is different. So the value which we have taken, actually, that's why the plot is coming like this. I think you can say that. Means if we will zoom out a little bit more in that JUR software, and we'll take out the more values, then I think the graph will more look like you will get some kind of a the variations, I think. So that's why I think it's because the value which we have taken the graph.
So I'll just ask one question. I think you mentioned it wrong when you mentioned that you do quadratic fit and linear fit to get velocity and acceleration.
Yes,
that's not correct. Even if you do quadratic fit, you still get only velocity. But since a quadratic fit means change of velocity with time, you can also get acceleration. Whereas for a linear fit, if you make a linear fit, then that means velocity is constant, which means there is no acceleration.
Okay. Yeah.
So any more questions? Okay, let's thank the group again and welcome the last group.
So hello everyone, this is Anjali and the topic of our presentation is coronal hole detection using fuzzy-based computer vision algorithm. This project is under the supervision of Dr. Sanmoy and along with the team members Mayank, Kavita, Ritika and Vashali. So let's move on. This is the outline of our program. Firstly, I will introduce you to the coronal holes. Then we will talk about the image segmentation followed by fuzzy C-maze algorithm. We will then talk about the data analysis and then finally the result. So you might have probably seen this picture. Last year it was posted by NASA. It showed that the dark patches there are called the coronal holes. So I will be explaining in the next slide. Okay, so what are coronal holes? A coronal hole is a temporary region of relatively less dense plasma in the solar corona, where the temperature is low and it's less dense. And the sun's magnetic field extends into the interplanetary space as an open field. Okay, so this magnetic field allows the solar wind to escape more readily into the space, resulting in the streams of relatively fast solar wind. Coronal holes can develop anytime during the solar cycle, but are more prominent during the solar minimum. Now let's move on to the characteristics of the coronal holes. They appear at dark areas in the solar corona. We cannot see them in the visible region because they're not visible. So we have to use the ultraviolet and solar X-ray images. Okay, so they are dark because they are cooler and less dense than the surrounding region. Also, they last between few weeks to few months. They are also found near the solar polar regions, extending towards the equator during the periods of low solar activity. And as I said, that these usually last during the solar minimum. So now Mayank will explain about the observation and study of coronal holes.
Space-based observatories like SDO, SOHO, Stereo. This is SDO, this is SOHO, and this is Stereo. Continuously monitor the sun in different wavelengths, providing image and data for studying the morphology and evolution of coronal holes. Coronal holes are based observed in extreme ultraviolet, EUV, and X-ray wavelength. Instruments like atmospheric imaging assembly AIA on SDO capture high resolution image of the sun's corona in EUV wavelength, providing valuable data to study and analyze coronal holes. Impact on Earth and the space weather. The high-speed solar wind from coronal hole can have several effects in space weather, like geomagnetic storm. Solar wind from coronal holes interact with Earth magnetosphere, causing geometric storm that impact power grid, communication system, satellites. Coronal hole solar wind particle interact the Earth magnetosphere, producing colorful display of auroras near the poles. These beautiful light shows occur when the solar wind particle interact with the Earth upper atmosphere. Coronal holes detection is important for space weather forecasting, spacecraft operation, understanding solar activities, assessing radiation risk, studying potential link between solar activities and the Earth climate, By monitoring and analyzing coronal holes, scientists can predict the solar wind stream, protect the spectrum, gain insight into the sun's magnetic behavior, and enhance our understanding of space weather impact on Earth and space-based system. Ritika will explain image segmentation.
Now coming on to the image processing part, we process the image to study various details in the image. So we do that by image segmentation, by which we basically split the image or group the certain pixels in the image using certain algorithms. We could do that by specifying boundaries or drawing lines. By that, we reduce the complexity of the image, and that makes the analysis easier. Now, what is the need for image segmentation? We could tell that by seeing the various applications in diverse fields, such as satellite images could provide us with the soil information, geographical contours, and security images. Even in medical industry, as well as even the face recognition system uses image segmentation. Now, these are some of the techniques that are used in image segmentation. In our code, we have mainly focused on the threshold method and the clustering based method. A few other methods are there as well, which are like edge-based segmentation, in which which is based on the discontinuity detection, and then region-based segmentation. We partition images in homogeneous regions, and artificial neural networks, which uses deep learning algorithms. Now coming on to the threshold method, we can see these two images, but they are very different from each other. Like how we have we do that we set a certain threshold value and compare the pixels in the images with that threshold value, and then assign certain labels to the pixels again. And it could be done by these three processes, like three different ways of doing thresholding. It's simple thresholding. We just replace the pixel in an image with a black or a white. And in this Otsu's binarization, it is mainly used in images which are bimodal. That means their histogram of pixels have two main peaks. So we take a threshold value which is in between of those peaks, and then replace our pixels again, and then get a certain image. And in adaptive thresholding, we divide the images in certain portions, and each portion we assign a certain threshold value. Now, coming to the next, that is the clustering based segmentation, in which we segment the images in certain clusters. We cluster them on the basis of groups of pixels which have similar characteristics. And some efficient methods are algorithms are k-means, c-means, etc. And we'll be discussing about fuzzy c-means clustering. It is an unsupervised learning method. That means we can perform it with raw data. And fuzzy here basically means not sure. So there are two types of clustering methods, that is soft clustering and hard clustering. If the probability of one data point belonging to a cluster is either 0 or 1, then we say it's a hard clustering. Or if we can assign any other value except between 0 and 1, then it's a soft clustering method. So in our code, we have used a soft clustering method, that is fuzzy c-means. Here C is used for the cluster centers that we'll define later. Now coming to the parameters, it's based on three parameters. That are, first is the membership value, that tells us the probability of a data point belonging to an ith cluster. That is a jth data point belonging to an ith cluster. And C is the cluster center, ith cluster center. And then we have another parameter known as the fuzzier, which is M, or we can say fuzzy index, which defines how fuzzy the boundaries of our cluster can be. Now coming to the algorithm, this is how we implement this method. First, we initialize a matrix of the assigned membership values, and then we update the cluster centers, which is basically an average of the positions. Then we update our membership value again, depending on the cluster center values that we are getting at each iteration. And then we stop this method when the change of these U matrix becomes very small. Otherwise, we repeat the process from the second step. Now, Kavita will discuss about the data download process.
Okay, now I'm gonna show you from where and how we downloaded the data. For the data, we use VSO, where VSO stand for Virtual Solar Observatory. Here you can see the interface. First, here we selected the instrument based upon our requirement. Then we selected, selected the search. After that, we selected the AIO instrument, which is one of the instrument of SGO that provides the solar atmosphere images in different wavelengths. After that, on the right hand side, and then you can, as you can see on the right hand side, we selected the date and time. And one important thing is that here, the data we used of the year 2017, because it was the time of solar minima. And as Anjali already mentioned that at that time, the coronal holes are more common and persistent. And here we selected the 193 Armstrong for wavelength, because in this wavelength, the contrast of the coronal solar holes is much better than in other wavelengths. After that, we requested for the data and then selected the URL file. And finally, we downloaded our data by clicking on this link. Now I hand over to Vaisali for the data analysis.
Thank you so much, Kavita. Now further, I will explain the data analysis part. Here we, as Kavita already mentioned, we downloaded the data from Virtual Solar Observatory, that is VSO. So the data was in FITS file. So yeah, and it was having dimension of 1024 cross 1024, and it was a 32-bit image. Then we plotted that FITS file. Actually, as my group members have already mentioned that coronal holes are visible in UV and X-ray. So there are basically three wavelength ranges, that is 193, 211, and 171 Armstrong. So we selected 193 because actually already mentioned that the contrast of the coronal holes are like quite better in that region. Sorry, in that range. So this is the FITS file image. As you can see, the variance of the pixel intensity is not like it's very low, right? So we cannot detect the coronal holes using this image. So for that, further we did the processing. So to plot or to find the coronal hole, we first found the maximum and minimum intensity values, which were like maximum intensity value for that image was some 7,844 point something, and minimum was in negative. So why it is negative? Because the image which we used, basically there are two types of images. One is data, signed and unsigned. So here it is a signed because so that its value can be in negative. So then we converted our original image into stretched image. Because the original like this we converted that because it is very good to visualize that data, as well as it highlights the main features, and then it is easier to process further, so and interpret also. So that's why we converted our image into stretched image. Then next, we set some, like already she mentioned, we worked on two processes. That is, one is two methods. One is threshold method and another one is fuzzy C mean method. Okay. So this is the first method in which we set some threshold value. Okay. So threshold value means what? First, we converted our intensity values from 0 to 255. Okay, so the minimum value will be, so minimum intensity value will correspond to 0 and maximum will correspond to the 255. Then we plotted this graph. Here we set our threshold value to 70. So below 70 will be considered as 0 and above 70 will be considered as 1. So we can change our values as our requirements. So we shown 3 plots here with the threshold value 70, 100 and 200. So we can easily detect the coronal holes as our interest. So next we map each. So from here we are starting with the fuzzy C main method. That was a threshold method, but it is not really convenient because it only works on 2 intensity values, that is 0 and 1. So middle values could be what about those values? So that's why we move towards the fuzzy C mean method. So here we map each intensity level to output intensity level. So this is the final image which we got from this one. Yeah. So the thing is that we performed this simulation on Python, and Python, if you perform this in MATLAB, then you will get right side up image. But we are performing in Python, that's why we are getting we got those inverted image. Sorry. So after performing the image axis transformation, we got this image. Then after applying fuzzy C method, we get this segmented image. So as you can see here, there is a very background, which will be considered as a, which will be there as a noise. Then the solar limb will be present there. Then other noise is also there. So that's why what we did, we generated a binary masked image. Okay, it's just a hole with the same pixel values. Then we take the difference of these two. So this is our fitted image. We subtracted this image from this, and then we received this image. So as you can see, the coronal holes are visible. The other noise part has already been removed. So now, yeah. So after removing the background, we received those coronal hole images, and this is our final result, in which we found it means that we detected the coronal hole. Then the conclusions are, the technique used for solar coronal hole detection is capable of detecting coronal hole region efficiently despite of presence of noise. There was very much noise in background, solar limb and all those. So we removed that also. And the next is, the methods do not require large database like other methods to generate a desired result. It was a quick data we downloaded from USN and we proceed further. And it is a totally unsupervised method, means no need of labeling data or anything. And yeah, so thank you so much, guys. Now we are open for questions.
So where you mentioned the fuzzy C-mean algorithm, right? So you use the parameter M, which controls the fuzziness of the boundary of the cluster, right? So what role does that play in it?
It's actually, it's present in the power of the objective function. So the more the M is, the more fuzzier boundaries you could resolve. But if it's very large, it means that there's only a one center and every point is very near to that center. So we cannot really resolve that. So
what do you mean by fuzzy boundary? Because it's the logic that is fuzzy, right? So what do you mean by fuzzy boundary as it?
fuzzy basically means vague boundaries or uncertain boundaries. So if it's a very sharp, it's a line, we could say it's a very sharp boundary between two things. But if it's not, then we are applying this fuzzy boundary, like soft clustering, that we cannot actually define very sharply that this is the boundary. So we are assigning one index to it that will determine how uncertain your boundaries are, and still you are able to resolve.
With respect to the center, right?
Yeah.
Can you go to the background subtraction one slide? Yeah, so I was curious about how did you subtract the background and obtain the binary mask in the last step? Yeah. Let me check this image. Hmm?
So with the Python,
Yeah, no, I am talking about the last image that you have obtained after subtracting the limb. Yes, the coronal hole that you have separated from that fuzzy means segmented image. How have you done that? That's what I'm asking.
Okay, so basically, after doing this fitted image is actually nothing but this is all is a background. Okay, this is the part which we received because as you can see here is the white background. So this background is this one. So this is just a background, not the coronal holes.
Yeah, that I
We already
understand.
did here, and then we only plotted the part which having low intensity.
Yeah, so for that you must have a intensity value, right? Do you? For you to separate two specific components over there, you have a noise which you call background, and you have your region of interest, right?
Oh.
So what is that specific factor which you used to separate your region of interest and your background? That's what I'm asking.
In the fuzzy method, we are assigning values to it like 0 and 255. So we're converting image into those two intensities. First, we are comparing it with that second image on the top so that we remove the boundaries that are unclear and the noise that is present on the top corners. Then, then we are comparing, then we remove the background. So we get that image at the bottom. From there, we again like select the certain pixels, like the brighter points we are rejecting and the
So
because we are
basically,
giving 2 points, right?
So-
So we are rejecting one point and just plotting the other, and the rest is all the background.
so basically you're doing another kind of intensity thresholding. Is that is what I'm understanding from your explanation? So it's what it looks like to me right now. It's the
kind of
roundabout way
similar,
of.
but there were other parameters as well, like M. We are taking M as 1 only in this case, so maybe that's why it's similar to that.
So you
But
did the fuzzy C means, then you again did intensity separation between the background and the holes. So-
value was 100.
Yeah. So if you look at that original image and this image, is there specific amount of difference? Means this algorithm, what is it doing extra? Is it like
Which image? The first image.
the first one in which you arbitrarily set the threshold value to 70 or 100 something?
In this, as you can see, like fuzzy means is a why were we using fuzzy means because here we can make a clusters now. In threshold, what we only had two values, 0 and 1, high or low. But here we can set like according to our choice, we can make a clusters out of them. So here we set three values. One is from 0 to 70, another was from 0 to 140, and third was 140 to some 255.
Okay.
70 to 1.
Okay, so it's multi-class image
Yes.
segmentation.
More questions?
So what are the criteria for selection of threshold value? I mean, how you, although you choose arbitrarily like 70, 100, but there should be something behind, no? Like,
yeah, we first plot the histogram of pixels, and then we see how many peaks are there, like what pixels are present, like what is the maximum and minimum. And then we take a middle value of it, and then it's like hit and trial method.
Actually, we plotted for various threshold values. Then we found that for this value, it is showing like very clear coronal process.
Okay, more questions? If not, let's thank the team. Okay, let's also thank all the speakers